I welcome all the mechanical engineering students which are studying the subject of IC engines in this semester, especially at the National University of Technology, Islamabad. My name is Ali Raza and I am lecturer at Department of Mechanical Engineering, National University of Technology, Islamabad. The subject of IC engine is being offered in the fall semester 2023, and these are the textbook which are IC engines by V. Gensen, and some are the reference books which we are using in this subject. The topic of today is supercharging and turbocharging. This is one of the most important topics in the subject of internal combustion engines. It is relevant to the power output of the engine and how can we increase by doing the supercharging and turbocharging, and we will see that what is the difference between supercharging and turbocharging, which one is better, types of supercharger and other things. So let's start from the introduction. It is a principal aim of any design engineer which is going to design the engine that the principal goal is the improved power output and the minimum exhaust emissions. Anyone who is going to design the engine, he must keep these two parameters in mind. And the power output of any engine depends mainly upon the following five factors. There are two types of engine. The first one is naturally aspirated engine, in which there is no components like supercharging and turbocharging. The power depends upon the following five factors. The first one is how much amount of air has been inducted into the engine cylinder, and then extent of utilization of the inducted air, that how much amount of air which is inducted is used actually for the complete combustion in the engine. The third one is speed of the engine. The fourth one is quality of fuel admitted and its characteristics. The word combustion characteristics is very important because there are different types of fuel, and it is almost impossible that all the fuels at different gasoline stations have the same combustion qualities. And the last one is thermal efficiency of the engine. It can be seen that the last two factors are interdependent and major modifications might be required to achieve the complete combustion and therefore may not be preferred method. The fourth and five are interdependent because if the quality of fuel is good, if for example if we are using the high octane fuel, then the thermal efficiency of engine will be high, and if we are using the low octane fuel, or we can say that sometimes the quality of fuel is not good and it will affect the efficiency of engine. So these two factors, fourth and fifth, are interdependent. And the brake power of the engine is given by equation 18.1. And let me clear that we are now learning the chapter 18 from the book IC Engines by V. Gensen. So in these equations, we can see that there are there are different parameters which are like brake power, brake mean effective pressure, swept volume, number of stroke, and number of cylinder in the equation of 18.1, which is the equation of brake power. And there are two factors in this expression. Apart from a number of cylinders and cubic capacity of the engine, which can increase the power output, they are one. The first one is number of power stroke, and the second one is brake mean pressure. Basically, it is brake mean effective pressure which is generated in the in the combustion chamber. So, for a given capacity, we can increase the power output either by increasing the brake mean effective pressure or by increasing the number of power stroke. And it must be clear to all that there is a limit to the increment of both these parameters. We know that in a four cylinder engine and in a four stroke engine, the number of power stroke in one in the all four strokes, and other three strokes are suction, compression, and exhaust stroke. So it is interesting to see that there is only one power stroke in the four strokes of a four stroke engine. However, by increasing the main effective pressure, we will see that there is a limit of increasing the main effective pressure, because it will create a lot of vibration and the pressure and temperature of the engine, and we have to see that how much we can increase the main effective pressure. So in one line we can say that if we increase the mean effective pressure of engine, we can increase the power output of the engine. So the most preferred method of increasing the power output is by means of increasing the main effective pressure. We can achieve this by giving the more amount of air or air fuel mixture at a pressure which is higher than the atmospheric pressure. This will increase the density, thereby the mass of air or air fuel mixture inducted for the same shaft volume. It is interesting to note that we are not doing any change in the swept volume of the engine. The swept volume of the engine is still same, but what we are doing that we are inducting the more amount of air fuel mixture in the engine. So what will be the result of this? We will get the high brake mean effective pressure, and then we can get the high power output of the engine. So at this moment, let us define the term supercharging. The method in which we can supply the more amount of air or air fuel mixture at the pressure higher than the atmospheric pressure is known as supercharging, and we use some device for this method. This device is known as a supercharger. So if I can read the bookish definition for supercharging and supercharger, it will be like the method of supplying air or fuel air mixture higher than the pressure at which the engine naturally aspirates by means of boosting device is called the supercharging, and the device which boosts the pressure is called the supercharger. So at this moment we have learned that why we are using the supercharger, what process is known as supercharging, and which device is known as supercharger. Let's move further. And what is the main purpose of the supercharging is that to raise the density of air charge before it enters to the cylinder. We can say that there may be 15%, 20%, or maybe 30% of increment in the amount of air that is being inducted in the engine cylinder. Thus, the increased mass of air will be inducted, which will then be compressed in the each cylinder. It is interesting that at the same swept volume, some more amount of air is being inducted in the engine. This makes more oxygen available for combustion than the conventional method of drawing the fresh air charge into the cylinder. And then consequently, more air and fuel per cycle will be forced into the cylinder, and this can be effectively burned during the combustion process to raise the engine power output to a higher value than that would be otherwise possible. It is like when there is a more amount of air and air fuel mixture, it will obviously give the high amount of combustion. There are some more important points in the process known as supercharging. Supercharging increases the power output of the engine. It does not increase the fuel consumption per brake kilowatt hour. This is the most important point. Sometimes we mislead the term supercharging by saying that supercharging can increase the fuel consumption, but it is not true. Supercharging does not increase the fuel consumption. Certain percentage of power is consumed in compressing the air. This power has to be taken from the engine itself. This will lead to some power loss. But in practical, the power produced by supercharging is more than this power loss. However, it is seen that net power output will be more than the power output of an engine of the same capacity without supercharging. The engine should be designed to withstand the higher forces due to the supercharging, because when there is a increase in pressure, it will create more vibrations and other thermal stresses on the parts of engine. The increased pressure and temperature as a result of supercharging may lead to detonation. Therefore, the fuel used must have a better antenna quality. So it must have high octane number or high cetane number. In practice, racing car engines use supercharging. The most important areas where supercharging is of vital importance are: the first one is marine and automotive engines, where weight and space are important. We know that in marine engines there is a lot of problem of space and power, because there is much more space available in the ships as compared to the ordinary trucks and buses. So we need a lot of amount of power to run that marine ship in the ocean. And then the second part is engines working at high altitudes. The power loss due to altitude can be compensated by the supercharging. Supercharger is a pressure boosting device which supplies air or mixture at a higher pressure. A centrifugal or axial flow or displacement type compressor is normally used for the supercharging. If the supercharger is driven by the engine crankshaft, then it is called mechanically driven supercharger. In this case, this supercharger is linked with the crankshaft of engine. Some superchargers are driven by a gas turbine which gets its power from the engine exhaust gases. Such a supercharger is called turbocharger. So we can see that there is not a much difference between supercharger and turbocharger. So at the moment, let's see the types of superchargers. There are three types of supercharger, which are centrifugal type, roots type, and the vane type supercharger. Here is a schematic diagram of centrifugal type of supercharger, which is commonly used in the automotive. Here we can see the different parts of supercharger. We have air inlet, and then impeller, diffuser, and then we have volute casing, and at the end we have outlet. The centrifugal type superchargers is commonly used in automotive engines as shown by this figure 18.1. And I should repeat that this figure is taken from the book of ICE Engines by V. Gensen from chapter 18. A V-belt from the engine pulley runs the supercharger. First of all, the air-fuel mixture enters the impeller. Here we can see that it is the impeller, and the air is entering at the center of impeller. It then passes through the impeller and diffuser vane. So here is the impeller, and these are the vanes of diffuser. And after that, finally, air or mixture enters the volute casing and then goes to the engine. So this is the volute casing, and from this outlet it is going towards the engine. The mixture will come out at higher pressure, and this condition is called supercharged condition. At this point, the pressure of air or air mixture is not much, but when it comes out at this point from the outlet, the pressure of engine is the pressure of mixture is very high, and obviously then the temperature will also be high. So because of this high pressure, more air fuel mixture is forced into the cylinder, and we can say that about 30% more air fuel mixture can be forced into the combustion chamber. and these are the impeller runs at very high speeds. And it is interesting to note that uh, the speed of these impeller are about 80,000 revolutions per minute. The impellers are running at 80,000 rpm. Thus, the impeller should be able to withstand the high stresses produced at this speed, because the speed of 80,000 rpm is very high. Impellers are usually made of duralumin or alloy steels to withstand the high stresses. So, this is the complete functioning of a centrifugal type supercharger, which is commonly, or we can say that mostly used in the automotive engines. And these are all the processes or qualities or characteristics of centrifugal type superchargers that I have discussed earlier. Now we have second type of supercharger, which is called Roots supercharger. The schematic diagram of Roots supercharger is given in this figure 18.2. We can see that the Roots supercharger has two rotors of epicyclic shapes. We can see that this is one rotor and this is second rotor. These rotors are of epicyclite shape, with each rotor keyed to its shaft. So here are two shafts. This is one shaft and this is second shaft. These rotors are keyed to the shafts. One rotor is connected with the other one by the means of gears. These two rotors are connected with each other by the means of gears. The gears are of equal size and therefore both the rotors rotate at the same speed. Due to the equal size of gears, both rotors have the same speed. The root supercharger operates like a gear pump. The mixture at the outlet of the supercharger will be at much higher pressure than the inlet. Here we have inlet and here we have outlet. And we can see that the schematic diagram of root supercharger is simpler than the centrifugal charger. And here we have another supercharger which is known as vane type supercharger. Uh, this is the third type of superchargers. Let's see the properties of this supercharger. There are a number of vanes which are mounted on the drum which is inside the body of supercharger. Here we can see that this is the drum, these are the vanes, this is the body, it is inlet and it is outlet of the vane type supercharger. These vanes can slide in or out against the force of the spring. Here a spring is attached with the each vane, and because of this arrangement the veins are always in contact with the inner surface of the body. These veins are in contact with the inner surface of body due to the force upon the spring. The space between inner surface of the body and the drum increases from inlet to the outer side. You can see that. And then in this way the quantity of fuel, the quantity of mixture which enters the inlet decreases in volume, because of which the pressure of the mixture will increase and it reaches the exit. In this way the pressure at the exit will be much higher than the pressure at the inlet. So these are the three types of supercharger. Now let's see some comparison between between these types of superchargers. The required characteristics of a centrifugal type supercharger is poor and suitable only for low speeds. The root supercharger is simple in construction, requires only minimum maintenance and has longer life. The vane type supercharger has a special problem of wear of tips of the vanes with time. It is because that due to repetitive contact of body and the veins, there is a large possibility that these veins get weared with the passage of time. Therefore, one has to take into account the application and then decide the type of supercharging for that specific application. Now, let's move towards the methods of supercharging. Uh, Normally, there are 4 to 5 methods of supercharging, which we will see here. The first one is independently driven compressor or blower, usually driven by an electric motor, and then ram effect. Third one is under piston supercharging. Fourth one is catenary system applied to two-stroke engines only, and then we have engine driven compressor or blower. Now we'll see the effects of supercharging. Before supercharging an engine, one should understand its effect. And let me clear that all the effects are not positive of supercharging. There may be some effects which we can take as a positive effects, and also there are some effective if they are not negative, but they do not have a good effect on the engine and other vehicles and other vehicle parts. Let's see them one by one. The first one is high power output. The second one is greater induction of charge mass due to high pressure, better atomization of fuel, better mixing of air and fuel, better scavenging of products. In this way, we can send out the exhaust gases in a very quick manner. Better torque characteristics over the whole speed range. We can get the more torque from the same engine with the same swept volume. Quicker acceleration of the vehicle, more complete and smoother combustion. It is because that when we are sending the air fuel mixture at a higher pressure, it also increases the temperature of mixture. That's why the combustion become complete and smoother. As you know that incomplete combustions caulking causes the detonation or knocking in the engine, and we can use the inferior or poor ignition quality fuel in this way. Smoother operation and reduction in diesel knock tendency, increased detonation tendency in the SI engine. It is because that when we send the mixture at higher pressure, it increases the temperature, and sometimes it happens that fuel is burnt before it is required. And then we have improved cold starting, reduced exhaust smoke, reduced specific fuel consumption in turbocharging, and increased mechanical efficiency. These are the some effects of supercharging. And here we have some negative effects, which is increased thermal stresses on the engine parts, increased heat losses due to increased turbulence. When there is an increase in temperature and pressure, so the turbulence will also be increased. And then we have increased gas loading, increased valve overlap period of 60 to 160 degree of crank angle, increased cooling requirements of piston and valves because due to high pressure and temperature, the requirement of cooling will also be increased. So we have to decide accordingly that how much supercharging or how much turbocharging we need to use in a safe range. Then there are some limitations to the supercharging. Let's see them one by one. Due to supercharging, thermal load on the various parts of the engine increases. So when thermal load on the parts of the engine increases, it will also increase the thermal stresses. In some engines, the piston crown is provided with a hollow space. Oil or water is circulated through this space, and thereby the piston crown is cooled. In an existing engine, if supercharging has to be adopted, one should first study the factors that limit the extent of supercharging that can be tried. It means that we must know that how much amount of extra air or air fuel mixture we need to send in the engine. We should not send an excessive amount of air or air fuel mixture up to the extent that that it may cause the problem in case of extra or excessive vibrations in the engine, and that will also increase the thermal stresses upon the engine parts. Now let's move towards the most important part of this lecture today, which is thermodynamic analysis of the supercharging. The ideal dual combustion cycle of a mechanically driven supercharged engine is shown in figure 18.4, and the corresponding cycle for a naturally aspirated engine is shown in figure 18.5. And let me clear that this is figure 18.5. This is the ideal dual combustion cycle for the naturally aspirated engine which have no supercharger device, and this is 18.4. At the left side we can see that here are some extra processes involved in this. This is the cycle of an no, this is the cycle of an engine which is using the supercharging. So let's explain them one by one. We can see that the pressure P1 represents the supercharging pressure, and pressure P6 and P7 is the exhaust pressure. You can see that these are the P1 and P6 and P7, these are the exhaust pressure. And then we have the area which is 9, 10, 11 and 12. This area represents the work supplied from the engine to the supercharger as it is mechanically driven. So when the supercharger is mechanically driven, this amount of power from 9, 10, 11 and 12, this area shows that this power has been given to the supercharger from the engine. That's why this work is known as negative supercharger work. And then there are different processes. We can see that from first of all we see the naturally aspirated engine which is at the right side. So we can see that the process 7 dash to 6 dash, we have represented the normal engine with dashes and the engine with supercharger without dashes. So from 7 dash to 6 dash, this process is known as induction, and then from 1 dash to 2 dash it is compression, and then from 2 dash to 3 dash and 3 dash to 4 dash it is basically heat addition. This is heat addition at constant volume, and this is heat addition at constant pressure. And then we have the last process from 4 dash to 5 dash, which is known as expansion, and then from 5 dash to 1 dash it is known as heat rejection. Now let's see all these processes one by one in the engine where a supercharger is attached. We can see that the induction process is from 8 to 1. In this process, the induction of air or air fuel mixture is being carried out, and then 1 to 2 is compression, and then 2 to 3 and 3 to 4 is heat addition, and from 4 to 5 is expansion, and 5 to 1 is then our heat rejection. But we can see that the swept volume in this figure is the same swept volume in the left-handed figure. We can see that both engines which is naturally aspirated, this one and this one which has supercharger, both have the same swept volume. But what is the difference? The difference is the mass of charge inducted in the supercharged engine is more than the mass of fuel or fuel air mixture inducted in the naturally aspirated engine. So it means that a large amount of mass has been inducted by using the supercharger. The supercharged engine inducts at a higher pressure P8 than the which is equal to P1 in this figure. So I have explained all these processes by the figures that we have seen just now. Let's have some look upon the work output of a supercharged engine. We can see that we have two positive work and one negative work in the supercharged engine. This is a negative work because this work has been supplied to run the supercharger from the engine, and then this is a pressurized gas exchange work, and then we have the third work. Let's see them one by one. The first one is engine work output, which is positive, plus gas exchange work, which is positive, minus the supercharger work, which is negative. Let's see the areas one by one from the PV diagram. So, if we talk about the engine work output, it is from 1, 2, 3, 4, 5, and 1. It is engine work output and it is a positive work. Plus, then the area of 8, 1, 6, 7, and 8. This is also a positive work, or it is also known as gas exchange work. And then we have a third one, or which is a negative supercharger work. We call it negative because the amount of energy has been supplied from the engine to the supercharger. It is from 10, or we can say that it is from 9, 10, 11, 12, and then 9. So the net amount of work will be from these two positive works minus this one negative work. It is to be noted that positive gas exchanges area may be greater than the negative area. We can see that this positive gas exchange area may be greater than this negative area. And further, it is to be kept in mind that with increase in supercharging pressure, the negative work will also increase, and therefore there will be a limit for supercharging. This thing we have also discussed, that we should not make the supercharger without any limit. The ideal efficiency of the supercharged engine will decrease with increase in supercharging pressure. However, it is to be understood that the net increase in power output is due to the increase in mass of charge at condition 1. So what we need, that we just need the increased mass at this point 1, and for this we use the supercharger. The density of charge at point 1 is greater than the density of charge at 1 dash for the same stroke of volume. And we can see that here we have point 1 for the supercharged engine, and at 1 dash we have point for the naturally aspirated engine. But the amount of air, or the volume of the air which is at this point, is more than the point 1 dash. And further, in naturally aspirated engine, actual engine, there is a negative work due to the gas exhaust process. And then it is to be noted again that the gain in output of supercharged engine is mainly due to increase in the mass of air inducted for the same swept volume. The additional mass of air inducted may also be due to the compression of the residual gases volume to the higher pressure. The rate of increase of maximum cylinder pressure is less than the rate of increase of brake mean effective pressure for supercharged engine. Thus, mechanical efficiency of supercharged engine is better than that of naturally aspirated engine. So we can say that due to this equation where m is greater than m dash, the mechanical efficiency of a supercharged engine is better than the mechanical efficiency of this simply or naturally aspirated engine. Now we'll talk about the power input for mechanical driven supercharger. This is the equation of power required to drive the compressor is given by. which is P is equal to m dot A Cp into T1 and P2 over P1. Basically, there are different parameters which are involved in this equation, and also work done is involved in this equation, where T1 is the initial temperature, P1 is the initial pressure, P2 is the delivery pressure, and in the last we have isentropic efficiency of the engine, which is, you can see from the equation, the equation of power which is given. This power may be supplied by the a separate drive by a motor or any other prime mover driving the supercharger, connecting the supercharger to the engine output shaft, exhaust gas driven gas turbine, which is called turbocharging. Or we can say that if a supercharging is being driven by the gas turbine connected with the exhaust, then this mechanism is known as turbocharging. So now let's talk about the turbocharging. In turbocharging, the supercharger is being driven by a gas turbine which uses the energy in the exhaust gases. There is no mechanical linkage between the engine and the supercharger. The major part of a turbocharger are turbine wheel, turbine housing, turbo shaft, compressor wheel, compressor housing, and bearing housing. In the next figure, it will be shown that what is the principle of exhaust turbocharging of a single cylinder engine and B type engine with charge cooling unit respectively. These are the figures, but we will discuss these figures in later. During the engine operation, hot exhaust gases blow out through the exhaust valve opening into the exhaust manifold. The exhaust manifold and the connecting tubing route these gases into the turbine housing. As the gases pass into the housing, they strike on the fins or blades on the wheels of the turbine. When the engine load is high enough, there is enough gas flow, and this makes the wheels of turbine to spin rapidly, and there is a minimum amount of pressure which is required to spin the wheels of turbine. The turbine wheel is connected to the compressor wheel by the turbo shaft. As such, the compressor wheel rotates with the turbine, which sucks air into the compressor housing. In this way, centrifugal force is generated, which throws the air outward. This causes the air to flow out of the turbocharger and into the engine cylinder under pressure. In the case of turbocharging, there is a phenomena called turbo lag. It refers to the short delay period before the boost or manifold pressure increases. This is due to the time the turbocharger assembly takes the exhaust gases to accelerate and the turbine and compressor wheel to speed up. So this phenomena is simply known as turbo lag. In the turbocharger assembly, there is a control unit called wastegate. This unit limits the maximum boost pressure to prevent the detonation in SI engines and the maximum pressure and engine damage. It is a diaphragm operated valve that can bypass part of the gases around the turbine wheel when manifold pressure is quite high. And now let's see some other parameters. The computer controlled turbocharging system uses engine sensors, a microprocessor, and wastegate solenoid. The solenoid, when energized or de-energized by the computer, can open or close the wastegate. By this way, the boost pressure can be controlled closely. It means the sensors which are attached, they control the everything about the supercharging, that how much amount of excessive air must be sent into the engine. The exhaust smoke comparison for a diesel engine for a naturally aspirated and turbocharged version for different loads can be seen in the next figures. There is an appreciable reduction in smoke in the case of a turbocharged engine and the overload operation. Now let's talk about some charge cooling. When air charge is compressed, it becomes hot. When air charge leaves the compressor, it is as much higher temperature than the ambient temperature. During supercharging, the temperature of air increases from 60 to about 95 degrees. When air gets heated, it expands and the density of air is reduces as a result. Because of this happening, the mass of air entering in the cylinder becomes lesser. This reduces oxygen availability in the cylinder for the combustion. Further, the supply of the hot air to the engine may increase the engine operating temperature, and as a result, the temperature of engine becomes very high. So, in such cases, charge is required to be cooled, and the charge is cooled by the way of intercooling and or aftercooling to overcome these problems. And however, this adds to the complexity of problem. There are some vehicles which use the intercooler to cool the charge. Now we have some figures. Basically, these are the methods of supercharging and turbocharging. In this figure, basically, this figure is 18.7a from the book. We can see that compressor, engine, and turbine are all geared together. Here we can see that there is a compressor, inlet compressor, and then we have engine and we have turbine. These all are geared with one line with the help of gears. The turbo compound airplane engine is an example. In this case, the turbine output is insufficient to run the compressor, particularly at part load. When the throttle is not at its full position, there is a problem to rotate the blades of turbine. Also, the additional power from the turbine can be fed to the engine. And if we see this figure, this is 18.7b. In this figure, we can see that the gas generator type of arrangement is being shown here. In this case, engine drives only the compressor, but if you see the previous figure, we can see that the engine and the gear which is attached from engine is being run the exhaust from the turbine and the compressor. The single shaft with the help of gear from engine is connected to both exhaust from turbine and inlet to the compressor. But if you see this figure, which is 18.7b, it is seen that engine drives only the compressor. In this arrangement, engine is only connected with the compressor with the help of gear shafts. Gears are mounted on the shafts of both engine and the compressor. Air from the compressor flows through the engine and the exhaust gases drive the power turbine. Most free piston engines work on this principle. And then we have now figure 18.8, in which we have shown the principle of exhaust turbocharging of a single cylinder engine. In the turbocharging, supercharger is being driven by the gas turbine, which uses the energy in the exhaust gases. There is no mechanical linkage between the engine and the supercharger. The major part of a turbocharger are turbine wheel, turbine housing, as we have discussed earlier. So the figure 18.8 and 18.9 show the principle of exhaust turbocharging of a single cylinder engine and a V-type engine with charge cooling unit respectively. You can see that it's a V-type engine and it's a single cylinder engine. During the engine operation, hot exhaust gases blow out through the exhaust valve opening into the exhaust manifold. You can see that this is the complete diagram of turbocharging of a single cylinder, and in the next we have the turbocharging of a V-type engine, where we have turbine, we have gases, and then we have compresses air, and it's a complete, you can see, a cycle which runs the supercharging. And because in this process turbine is being run by the exhaust gases, so this process is known as turbocharging. In figure 18.10, it's a graph. We can see that there are two types of engine, and the graph is drawn between the load and the exhaust smoke. We can see that when we use the turbocharged engine at full load, the exhaust smoke is about 25 to 26%. But when we use the naturally aspirated engine at full load, we can see that exhaust smoke is about 80%. So there is a difference of about 55 to 60% in case of naturally aspirated engine and turbocharged engine. It means that when an engine is turbocharged, the amount of exhaust smoke is reduced sufficiently. So this is some workout example, and we'll do it in the next part. Thank you. And if you have any questions, you can ask me in the comment section. Thank you.